Good afternoon, I'm Peyton Ulrich, and I'm going to be presenting on partial least squares regression analysis. First, let's go over a quick review of regression analysis in the univariate case. Typically, we use regression analysis to analyze the effect of one or more continuous explanatory variables on a single continuous response variable. When performing multiple linear regression analysis, we use the following model where each of the beta terms represents a slope coefficient and each of the x terms represents one of the explanatory variables in the model. In multiple linear regression, the least squares method is typically used to estimate the slope coefficients while minimizing the sum of the squares of the residuals. Now let's suppose we no longer are interested in only a single response variable, but instead want to analyze the effect of our set of explanatory variables on more than one continuous response variable, hence entering the multivariate case. Additionally, let's suppose that we are working with data in which the explanatory variables are highly correlated and we want to account for these relationships. In this case, the partial least squares method of regression analysis is appropriate. The partial least squares model is shown below, where y is the response matrix of dimension n by m, x is the predictor matrix of dimension n by p, b is the coefficient matrix of dimension p by m, and e is the noise term with the same dimensions as y. Please note that in this case, n is the number of observations, m is the number of response variables, and p is the number of predictor variables. In the partial least squares method, the underlying model separates variation into two categories, outer relations and inner relations. Outer relations are the relationships within the x and y blocks individually. In other words, the outer relations are the relationships between each of the explanatory variables and between each of the response variables. This is shown by a decomposition of x and y, like in principal component analysis, which we covered earlier in this course. Interrelations are the relationships between the x and y blocks, or how the explanatory variables affect the response variables. This is shown by performing regression between t and u, which are the decomposed versions of x and y. In partial least squares, our objective is to decompose x and y while taking into account how x affects y. This is done using matrix algebra and an algorithm called the NIPALS algorithm. The final model is shown in the form here, where either on the left the model is using mean-centered and scaled data, and on the right the data would not be mean-centered or scaled. To demonstrate how partial least squares regression can be used, let's consider the following scenario. Suppose a teacher gives their students a midterm exam and asks each student to report how many hours they spent studying for the midterm and how many hours they spent watching Netflix. The teacher then wants to see how the student's time management affects their test performance. However, instead of simply using the overall score on the midterm as the response variable, the teacher uses the score on each part of the midterm as two separate response variables. Data is collected for each of the 10 students in the class, as shown in the table below. First, we can look at the outer relations in this model. As we can see from the scatter plots and the corresponding correlation coefficients, each of the two response variables in this model are highly correlated, and each of the two explanatory variables have a moderately high correlation. Additionally, using the PLS depot function in R, we can see the following decompositions of x and y. We can then examine the inner relations in this model by performing regression between u and t. Finally, we can use the PLS depot function in R to find a prediction function for this model. To demonstrate how we use this function, let's suppose we want to predict the test scores for a student who spent 4 hours watching Netflix and 5 hours studying prior to the exam. These inputs can be stored in a row vector, and we can calculate the expected scores for the student. As we can see, this student is expected to score a 75.6% on part 1 and a 77.8% on part 2, based off of the model that we arrived at through partial least squares regression.